just realized I forgot to put up the recording from last class, so I'll get both of those posted today after we are done. Couple things before we jump into things. So we've kind of got those remaining two Excel homeworks, the one due at the end of the day today. So, or not, sorry, not today, next week. That's kind of the 2 days for both of those. You also have that connect. Once again, I'm dropping the lowest. So if you're happy with your grade currently on the first 4, then if you don't do the 5th one, will be the one that gets dropped. So I moved the last connect assignment. Where is that? There you go. In there, so it's now kind of factoring in your grade. I also kind of went through I think everything I took as a connect should kind of be, you were missing them. They're now in there as zeros. Now, this is the last day I'll use iClickers. So early next week, I will get the grade on Canvas to reflect dropping your 3 lowest iClicker grades. So currently it's counting all of them, right? So next week, I'll basically replace this with something I upload where I have to drop the 3 lowest in my grade book off of Canvas, and then upload it so that you'll kind of see what your iClicker grade is with those 3 lowest drops. So that'll be happening probably Monday or Tuesday of next week. But currently, like I said, you can see what your connect score will be across those first 4 connect. If you're happy with that, you don't do the 5th one, that'll be the one that gets dropped. Other than that, I don't think there's anything else that I had. Any questions for me before? Oh, there was one more thing. I put up some practice materials for the final. So there's 2 kind of practice exams, the formula sheet that you'll have. So those are there kind of sitting for you next week as we kind of start getting closer and closer to finals week. Okay. Any questions for me before we jump into material here today? Okay. So we will pick up where we left off. I think that where I had left off was we had just ended talking about kind of this R squared, right? So we looked at a little bit how we do these regressions in Excel. We'll focus a lot more on Excel today. I'll just kind of use it as a tool to show you what we're doing with linear regression. And we're really going to focus on this idea that I brought up last class, which is what we're really picking up, right? When we estimate these lines, or we estimate these lines of best fit or these coefficients. So this is still interpreted as the correlation between that X and Y variable. Now, the way we interpret it, it kind of comes across as though I'm saying, X goes up by 1 unit, the predicted Y changes by whatever this coefficient value is. That kind of sounds like I'm saying it's causal, right? X is causing Y to change. So we want to be careful. Anything we're going to do in this class, we're not going to get to the point where we can identify causal relationships. All we can say is that we're picking up evidence of a correlation. Now, those correlations can be stronger, right? So we said if I include, additional variables here on the right-hand side, I'm still getting evidence of a correlation, but I'm getting that correlation holding constant all these other factors. So I'm getting closer to that causal relationship. But to truly be causal, we'd have to do some stuff with regression that's kind of outside the scope of this class. But at least that as we're adding more variables on the right-hand side there, we're getting closer to being able to interpret this as a causal relationship. So we went over these examples last class, where we said, if I run this really naive regression of whether or not the mother smokes on birth weight, that whether or not the mother smokes variable is going to pick up the effect of a lot of other variables that are correlated with that, right? So it might look like it has this huge negative effect, but that's because smoking during pregnancy is correlated with lower income, lower education levels, which is also correlated with lower access to healthcare, high quality foods, etc. Right? So we want to make sure that we're not kind of running these naive regressions. If we have the data, we want to control for things like mother's education, mother's income level. Right? So this is always the correlation versus causation. So maybe Y is causing X, X doesn't cause Y. I don't remember if it was this section or the next section I had a question. It's sometimes hard to know the relationship, like which way is it going, right? So, what's a good example? Well, I can use it like an econ example where I'm looking at price and quantity data. Is it the higher prices that are driving lower quantities, or the fact that there's lower quantities being purchased is actually resulting in kind of a lower price? I don't know what that direction is, right? And so sometimes we have this Z is causing both X and Y. If I leave Z out of the regression, I get some really screwed up coefficients, right? If I leave out those mother's income, mother education levels, I don't get good coefficients. So I used to think correlation implied causation, that I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it was the fact that I was already of a higher intellect, that I took the statistics class, and maybe that higher intellect would allow me to understand that difference, right? So I think another really good example of this is if you don't control for any other factor, and like let's say I was looking at autism rates and organic food sales data. If I run a regression using that data, it will look like organic food sales as they increase, so does autism. I don't think anyone would argue organic food is causing autism rates to increase, right? It's probably that there's other things that are correlated with both of these variables that were not factored, right? Like an increased attention to health, right? So we're just getting an increase in diagnosis of autism, but we're also getting people to spend additional money on kind of their food source. And we didn't control for that, right? So, don't worry about writing any of this stuff. But and I will say, as we kind of go through some things and we're doing these interpretations, some of the examples and things we'll work through aren't necessarily in the slides. It might be good to kind of be taking notes on some of this. It's a little bit more the other stuff we do in the class, and usually have the formulas up there and kind of working through them. But this is basically just a fancy math proof that if I run a really naive regression, just one X variable, the coefficient estimate that I see, that slope estimate, will include the true relationship, but also this bias component. Right? So this bias component is essentially picking up the fact that, yeah, if I leave out these other important variables, they might be correlated with the variable I've included. I might be picking up not just the relationship of this X1 variable, but the relationship of X1 and X2. Right? So if I include X2 into the regression, right, the second variable I think matters, this bias goes away, right? So we'll kind of get a pretty good example of this, I think. At least I think it's kind of a fun example, which is this GPA in athlete, right? So I'll give you these equations, and we'll kind of go to Excel here. So we did this a little bit last class with like SAT scores. So sometimes we'll write kind of A and B like these betas. I think I mentioned that last class. Maybe I'm interested in, my initial question is, what's the impact, right, of being a student athlete on that student's GPAs, right? So you go one of two ways. So there's like a bunch of literature on this where you're like, being a student athlete is, teaches you early on in college time management, right? And so, it also kind of, there's maybe some additional resources. You have kind of a built-in social group that you maybe can kind of assist you along the way. And so maybe there's some positives. It also takes a lot of time, right? I always tell, maybe I've told it in this class already, but like I when I was at undergrad at Purdue, I had like 4 or 5, like almost all my classes with this one long snapper on the football team. And we had like projects, and we were in the same group, and like trying to find a time to meet with him in the fall was like impossible. I mean, it was just between watching films, workouts, probably like his schedule. I don't know how he did it, right? And so this time commitment could also make being a student athlete really not a good thing for your GPA, right? It's just a lot of time. So we have this question. We're going to go into this kind of naive. We might run this regression, right? Well, we're then going to say, okay, look, if this data comes from D1 universities, and you can, I'm not out of pocket with this, the data that will show this. What do you think is probably true about Division I football players relative to the regular student body when it comes to academic kind of, admission standards? What might I do for a student athlete that I wouldn't for a regular student? Yeah, I might lower those standards a little bit, right? I mean, they're bringing a lot of revenue to the university. The university cares about having a high quality student body, but they also care about making money, right? And so if I have Division I college data, I might say, well, look, I know that these student athletes might just on its face might be coming in with a little bit lower kind of academic threshold, right? So if I really want to know the effect of being a student athlete, I need to control for that. I don't have a perfect control, but SAT scores are a pretty good one, right? I could use high school GPAs or something like that as well if I had that data. I think in the data set we have, I've just got SAT scores, right? So we can kind of look at it and say, okay, once I include this additional variable, I think it really matters for predicting GPAs. We looked at it a little bit last class. Maybe I get a completely different coefficient here. So let's see how this plays out. So we'll kind of go through and work with this GPA omitted variable data, right? So we were using this a little bit last class. This sheet 1 has just the original raw data. We're actually going to replace these. So I'm just going to delete these, and then I'll kind of repost it with everything that we did in class. Okay. So we start out, and I'll zoom in so we can see things a little bit easier. We talked about last class. If you have a Mac, you go to Tools, and then down to kind of your Excel add-ins, and make sure that you have the analysis tool pack selected. PC, you go to File, Options, Add-ins, manage those add-ins, make sure your analysis tool pack is selected. Once you do this once, you don't have to do it again. You now go to your data tab. That data analysis should be there on the right-hand side. Okay. So once again, if you're on a Mac, it's Tools, and then you kind of go down to your Excel add-ins, make sure that analysis tool pack is selected. PC, File, Options, then go to add-ins, make sure that analysis tool pack is selected. Okay. So here I'm going to start out with this very naive regression. So I go to my data analysis, go down to regression, hit OK. My Y variable, right, that left-hand side variable that we're trying to predict is going to be college GPAs. So I select that variable. I can select on the name of it. I hold Control-Shift, Command-Shift on a Mac, hit the down arrow, it selects the entire column. Right? I then go back. Okay, what's my X variable here that I'm interested in? Well, we're going to run this really naive regression, which is just whether or not they're a student athlete. Right? So I'll select in that athlete variable, Control-Shift, Command-Shift on a Mac, hit the down arrow, excuse me. Make sure I said, oh, I selected the labels, right? If I don't hit that button, I get this error that there's non-numeric data. Okay, I did select the label so that I kind of had the names associated with the variables. I'll put it on a new worksheet, hit OK. I'm then going to rename this so that when I post this, we can kind of, this is like my really naive regression, right? So zoom into these results, and we can kind of look at this and think about how we do this interpretation. So I go down to this athlete coefficient, and it's what, negative 0.28. So this is one where if I've got a 1,0 variable, we always interpret this coefficient as a 1 unit change in my X variable causes the predicted Y to change by whatever that coefficient is. Well, here are the units. I just got a 0, 1 variable. It's going from the 0 group to the 1 group. So not being a student athlete, going to, comparing to not being a student athlete, being a student athlete, right, belonging to that 1 group, would decrease my predicted GPAs by 0.28, right? GPAs on a 0 to 4 scale, that's a pretty sizable decrease, right? So I might look at this and say, yeah, no one should be a student athlete, right, if you're really worried about your grades. But I know this is a pretty naive regression. There's a lot of other things that matter. There's a lot of other things that would be useful to predict GPAs, right? So we also kind of see here, if we run this naive regression, this p-value, anytime I see this e to the negative, remember that means move the decimal 9 places to the left. So this p-value is pretty much 0. We always reject the null if the p-value is less than alpha. What's our null? We said we're always going to start out assuming that these slopes are equal to 0. Right? So if I can reject the null, I essentially am rejecting that there's no relationship, which said differently, I found evidence that there is a relationship, right? This slope is some value other than 0. Okay. Any questions on anything? We talked a little bit about all this kind of last class, but just in a different example here. Any questions on any of this before we keep moving? Okay. So the next thing we'll do is we'll go back to our regression tool. And notice this is kind of nice. It leaves in whatever you selected last. So I've already got my GPA variable selected as my dependent variable. Now what I'm going to do is I'm going to include both SAT and whether or not they're athlete. Okay? So I'm going to select this variable, actually select both of them, sorry. Control-Shift, Command-Shift on a Mac, hit the down arrow. Now it's, oh, I was in the wrong box. Oh, that's unfortunate. Sorry. So I have to reselect my dependent variable or that Y variable. Sorry. Now when I go to my X variable here, that's where I want to select, right? I've got X variables now, right? I've got multiple variables on that right-hand side, okay? Control Shift, Command Shift on the Mac, hit the down arrow. Notice it now puts in kind of both of those columns of data. Now I've selected my labels, right? And so the reason why selecting those labels is important is because once I start to include additional variables, if I don't, I'll show you what it looks like in a second. If I don't include the labels, it's just harder to kind of interpret. So it now kind of lets me know what those variables are, right? So now if I look at that student athlete variable, now what's the interpretation? Well, now holding constant everything else in regression, so holding constant the SAT score, now going from not being a student athlete to being a student athlete only decreases that predicted GPA by about 0.05, right? So I mean, that effect went really, down dramatically, right? Also, if I'm looking at my p-value here, can I reject that there's no relationship? Not at any of my conventional levels, right? 0.26, that p-value, not going to be less than my kind of conventional alphas of 0.1, 0.05, or 0.01. So not only did the effect dramatically decrease, I can't even say that there is an effect now, right? Not at 90, 95, or 99% levels, right? So just including one additional control variable completely changed what we would think about being a student athlete, right? Any questions on that? Is that making sense so far? Now, when we think about R squared, remember I mentioned this certificate of R squared from my class. I said R squared was essentially how much of the variation of this Y variable, so how much of that kind of variation in GPA can we predict using the X variables or those right-hand side variables that we included? So if I go from my first naive regression, I go up here, I only had an R squared of 0.008. So I was explaining the proportion of variation I was explaining was 0.008 or 0.8%. That's pretty low, right? That means there's 99.2% of the variation GPA I can't explain. That probably means I've left off a lot of really important variables, right? If I include SAT, what should happen to that R squared? Yeah, if I've got more variables that I'm using to predict GPA, I have more information, I should be able to explain more of the variation, or I should be able to make better predictions. So hopefully, when we go back over here, and this was just adding in one control, if I go up to my R squared, sure enough, it went from 0.008 to about 0.17. So it's still kind of low, right? I'm only explaining about what, 17% of the variation now, but I've only got two variables, right? That meant SAT score like explained about 16% of it. Like SAT appears to be really matter, right? Or at least be a pretty good predictor of GPAs here. Any other questions before we keep moving here? To start talking when we do regression stuff, I enjoy it, so I think I sometimes get a little bit too excited, and so stop me if I keep going. I do want to show you real quick why selecting those labels is helpful. So let's say you're like, I always forget to select the labels box. I'm just going to select the data, right? So I select that college GPA data. I then go over here, and let's say I select a bunch of variables, right? Hit OK. Well, this is why it's a problem if we don't select our labels, because it just labels them as X variable 1, X variable 2, and then I have to go back and remember, okay, what order were those variables in? So it's just easier to select the labels. That way, when you get the output, where is it? You kind of have, oh yeah, this coefficient is associated with the SAT score variable. Okay. Questions on this before we keep moving? So just as kind of a reminder, how would I interpret that SAT score coefficient? So the general interpretation is always a 1-unit change in our X variable causes the predicted Y value to change by whatever that coefficient is. So here, how would I, in this context?
Every increase in the SAT score increases their GPA.
Yeah, so for every point higher someone gets on the SAT score, the predicted GPA goes up by about 0.002 around. Now, that's really small, but that's also 1 point, right? We said, what if I want to know the effect of 100 points? What do I do there? If I know the effect of 1 point, simply, yeah, multiply it by 100, right? So, you know, a lot of times, like I would teach in a sports econ course, and we like talk about, you know, salary or like expenditures. And sometimes it's like, yeah, well, the effect of $1 additional is going to be so small, we have to scale it up. I mean, we're looking at the standard deviation of the expenditures for like athletic programs, and they're in the millions, right? So, you know, it's not unreasonable to see $1 million increase. Well, if we know the effect of $1, when we think we have this kind of linear relationship, just scale it up by multiplying it by whatever kind of increase you're interested in. Okay. All right, so we'll go back to this data and we'll do one more thing. So I'm going to go down to regression again. I'm going to reselect this variable so I don't have the issue where I don't have my labels. So college GPA is our Y variable. I'm now just going to, include every single variable here. I'm not going to include this SAT squared. I use this data in some other classes. We're not going to deal with squared terms, at least maybe next week. I'll kind of show you how we can use those. We'll just go all the way over to high school size. Hold Control Shift, hit the down arrow, make sure we have our labels selected. And here we've got, I'll call this one, right? We threw everything that we had at this regression, right? All the data that we had available, we used as our controls, our X variables. So including all these additional variables, I did increase my R squared, but you know, when we interpret these coefficients, we still interpret them the same way. But if my R squared is only about 0.3, I need to be, you know, somewhat cautious and say, well, look, I know that leaving variables out can mess up or bias my coefficients. If I've got 70% that I still can't explain, there's probably some important variables I'm leaving out. I should just be a little bit cautious when I'm looking at it. I should say, you know, these could change if I had all this additional, you know, all these other control variables that aren't in my data set, right? But 30% is not bad, right? R squared is about 0.3, so we're explaining about 0.3 proportion of the variation, or 30%. If we go down now, we'll kind of do a couple things, right? So for one, we've got all these coefficients, right? I just want to kind of highlight the student athlete variable now, because that's kind of the original story we started out with. Now, it looks like the effect of going from not being a student athlete to being a student athlete actually increases GPA, holding constant everything else in regression. And that's a lot more powerful, right? So the idea when I say holding things constant, this is the thought experiment is like, and the data essentially is doing this behind the scenes. It's kind of hard to conceptual understand this, but really what you're doing with regression or holding everything else constant is like saying, if I could have two high schools with the same size, two students who went to high school with the same size, two students who have taken the same total number of credit hours, they're, you know, both of the same demographics, right? Racially, gender, they both have the exact, went to high school, and they had the exact same rank in high school. They both scored the exact same on this verbal math test that they had to take to get into university. They both are either, you know, they both have the same SAT score, but one of them is a student athlete. That student would expect to see a 0.17 higher GPA, right? Or we would predict that their GPA is about 0.17 higher. That's a pretty powerful statement, right? Once we can kind of control for all these other things. So that's why more data, more variables are always good, because, you know, holding everything else constant, like I said, you're getting closer to actually being able to think about this as a causal relationship, right? If I can control for a bunch of other factors, you know, this is getting closer and closer to not just being a correlation, but closer to a causal relationship. And, you know, controlling for all these additional things, we completely flipped the story. We started out with our naive regression, thinking that it was a bad thing to be a student athlete, right? We include all these other factors that probably are you know, might matter, might be good at predicting. Excuse me. Now it looks like it's actually a beneficial thing. This is the idea of kind of the time management skills, things like that. What else do I want to say here? I think we're good. Any questions before I kind of move on to the next? We didn't really talk about this last class, right? And I'll start out with a naive one to kind of make this point, and then we'll kind of come back to this where we have all of our additional controls. So when we just had, well, actually, we'll do the one control. It's a little more interesting. When we just had SAT and whether or not they were student athlete as our predicting, predictors here, what we essentially had was all these coefficients. So I can write these values in. So my intercept was 0.68. I'm going to round these a little bit. Being a student athlete was what? Negative 0.05. And then 0.002 was the impact of the SAT score. Once I have these coefficients, if I plug these in, I can start to make predictions for this different y variable, for different hypothetical values. So I could say, look, if there was a person who was a student athlete and they got a 1200 on their SAT score, based off of this regression, what would I predict their GPA to be, right? This is a simple equation, right? I mean, 0.68 minus 0.05 times 1 plus 0.002 times 1200, right? Once I plug those coefficients in and this hypothetical kind of person's X values, I can make predictions pretty quickly. So, in Excel, I could kind of do this like, well, take my intercept, add to that whether or not they're a student athlete, and I said that they were, so times 1, then add whatever the effect of a 1 point on the SAT score is, times whatever that hypothetical person's SAT score was. All I'm doing is like a linear, this number plus this number and this number plus this again. It's nothing crazy here, right? Just one kind of long linear equation. Okay? And now I've got this hypothetical person's predicted GPA would be about 2.9. And I could play around with this, right? I could change 1200, I could change all these other values. Any questions on this before we keep moving? Make it a little bit harder. So let's say I've got this kitchen sink example, and I'm just going to delete some stuff here. We're not going to really use these, but you might be able to kind of envision. We're always getting these confidence intervals. So like if I was having test statistics and p-values, I could also build confidence intervals for coefficients. It's just that we typically only really are concerned with, is there an effect or not? Oh, I erased it. So we always kind of just have, is that slope equal to 0? So we're not going to really, in this class, use these columns. So I'm just going to delete them to make this a little more succinct, right? So let's try to come up with a predicted GPA for this hypothetical person, right? We'll come back to the intercept in a second, but let's say, I don't know, they've got 1100 on their SAT score. They were a student athlete. I forget how this verbal math test is scored now. I think it's between 0 and 1. It's kind of goofy. Yeah, so let's say, I don't know, they got a 0.75 on it. Let's say their rank in high school, they were 25th ranked in their high school. Let's say they were male. So if they're male, what value would this female kind of indicator variable be? Just 0, right? Let's say that they're white, right? Which kind of make, the black identifier is 0. Total credit hours, I don't know. Let's say they've taken 50 up to this point. And the high school size is also a weird one. So if you go back, I think this is like supposed to represent, I think it's hundreds, makes sense here. Yeah. So let's say, I don't know, 3.5. So I don't know, they went to a high school with 350 people or something like that, right? So, I said 350, but I just told you they're writing it as that, right? So this is kind of the size of the high school. So I've got this hypothetical person. I've got every single value, and this could, I say hypothetical, this could be an actual person. If I was an admissions department, I would be collecting data, run this regression, and then every single applicant, I would plug their numbers in and say, what's their predicted GPA, right? Are they going to be successful when they come to this university based off of the data, right? But for us, it's a hypothetical person, right? It's not, we didn't get this from an application. So then what we're going to do is just a longer equation, right? We're just going to go through every variable, take its coefficient, multiply that by the hypothetical person's value for that X variable, and then add them all together. Now, the one thing we don't want to forget also is we also need to add in that intercept. So kind of a nice, easy way to do that. I always just would, if I was working through this, put a 1 here. That way, if I take the intercept, multiply that by 1, it's just the intercept, right? I'm just making sure I get that added in. I'm then going to create for every single variable, right? Take its coefficient. So when I copy this down, I'm going to take the SAT score coefficient and then multiplying that by this hypothetical person's SAT score, right? So copying this down, I basically just take every single variable's coefficient and multiply that by that person's hypothetical value for the variable associated with that coefficient. So if I set this up kind of in this column right next to my regression data, it's pretty easy to kind of get all these different components. Well, now what do I need to do? Simply add them all up, right? I have to take every coefficient times the hypothetical value, add to that the next coefficient times that x value, plus the next coefficient, so on and so forth. How can I do that in Excel? What function do we have just to add things up? Yeah, right. So I'm just going to say, take the sum of all this. There's my predicted GPA, right? And if I wanted to, I can then go back in. Okay. Oh, actually, sorry, we sent over the wrong records. This person actually got a 1300 on the SAT, right? Oh, sorry, there was something. Next semester he's taking more. I don't know. There's more credit hours, right? You can go in and just kind of start playing around with these values. Right? So, like I said, if I was in admissions department, why not use some previous data to see how are all these factors kind of correlated with student success once they're at the university? And then I can kind of predict what every student kind of, admit, or every applicant's kind of predicted success would be. Now, obviously, it's still a prediction. We said the actual Y variable has all this stuff plus this error term, right? So yeah, we should use it as a guide, but for any one student, right, they might be able to outperform that prediction, right? Or underperform with that prediction, right? We don't know if the error is positive or negative there, but we can at least come up with a pretty good prediction as long as we have quite a few control variables there on the right-hand side, or predictor variables. You can kind of think about that way. Any questions how I set this up, or you want to see a cell again, or something I did maybe a little bit quick? So you can kind of think about this. We were taking the coefficients and just multiply them by the hypothetical values for those x variables. Any other questions on this before we kind of get out of Excel? Actually, there's one more thing I would want to do in Excel, because this will help you. I think this should be all you need for that Excel assignment, that 5th Excel assignment, if you want to kind of complete it. I can also pretty easily or pretty quickly come up with my rejection decision. So here I'm going to say, I don't know, I'm going to choose an alpha of 0.01, right? So which of these variables could I reject the null at, right? Now, if I'm rejecting the null, remember, I'm rejecting that there's no relationship. Well, I know that I reject, also mention something here in a second, if the p-value is less than alpha, okay? So if my p-value is less than alpha, I should have that earning memory. I can reject the null or reject that there's no relationship. Well, I can go through these and, where is that? There it goes. I can go through these and do this by hand, right? And I'll tell you a very common mistake on that with Excel, but also just kind of in general when we're looking at Excel output. If a p-value has e to the negative, what is that p-value? 0. Treat it like it's 0. If your p-value is 0, you're always going to reject, right? So anytime you see this e to the negative, it means it was so small that Excel had to kind of put it in this scientific notation. We're always going to be rejecting those. So I see a lot of people, they'll look at these and be like, oh, well, my p-value of 5 is not less than alpha of 0.01. First of all, can a p-value be 5? P-value is a probability, right? It's that kind of area in the tail, right? And so it has to be between 0 and 1. So I knew I did something wrong. Oh yeah, e to the negative, it's a really small value. A nice way to not make that mistake is if I use my if statement, all I'm going to do to see which of these variables can I reject the null for? Which of these variables can I say that I can reject that there's no relationship, or I found evidence that they are strongly correlated with GPA or my Y variable? Well, if their p-value is less than, and here I kind of have this set up where I've got alpha over here in the cell. If that's true, put the word reject here. If that's not, we'll just put the word fail for fail to reject. Now, when I copy this down, it's going to then update to the next variable's p-value, the next variable's p-value. What else is going to update? That alpha cell reference. So I always want to be comparing to that same alpha value. So I'll go in and freeze that. Now, when I copy this down, I don't have to worry about making this mistake where I read the scientific notation wrong, or I don't know, zeros get hard sometimes, like comparing 0.01 to 0.001 or something, something like that. This will kind of be able to do the math for me. All right, so it kind of prevents me from making these human errors. Right? Hit enter, copy this down. I now see I can reject that for, that there's no relationship for all but 2 of these variables. So only 2 of these variables look like they're not great, right, at predicting GPA, that they don't matter as much. Those variables are this verbal math test. So if I'm a admissions department and I see this, I'm like, well, why are we wasting our time with this test? It's not even a good predictor of if the students will be successful or not. And then if I come down here, also kind of one of our racial demographic that doesn't really tell us anything, right? So it looks like here, once I control for all these other factors, race isn't really playing a role in GPA, right? That makes sense. Any questions on that? Does that make sense? Like I said, if you really want to, you can go through and do this one by one. And on the exam, I might give you some Excel output, and you will have to just kind of look at it and say, okay, which of these have a p-value less than 0.01? For all of those, I can reject them. Right? I can say that I reject there's no relationship, or I found evidence there is a strong relationship. But if we're doing this in Excel, we can do that pretty quickly, right? Kind of just using that if statement, right? You could do it by hand if you wanted to. It's just, when I have 10 variables or whatever, it's kind of easier to do it this way. Okay. Any questions on this before we keep moving? All right. So let me save this, and I will post this after class. All right. We'll come back here. We already kind of looked at this. We looked at all this other stuff. So how much time do we have left? I might save this for this class. Okay, we'll start this. We probably won't finish it, but we can start the idea. And if we don't finish it, we'll finish it up on Monday. So assume that we have it instead this example, and initially it'll seem kind of stupid, but I'm eventually going to get to something I think is pretty interesting, which is how does athletic success kind of impact the academic standards of a university, right? And we'll kind of think about this, how we can achieve this. So what I might want to do initially is think about, okay, well, if I'm an athletic department and I want to increase my athletic department's success, right? And whatever sport I'm kind of looking at. How does spending additional money increase the likelihood I have success, right? Or how does that increase my success? So here, what we're going to do is set this up. And I think I called it round one in the slides, but like, basically, we're going to have this 1-0 variable, somewhat recent too, where it's a 1 if that basketball program made the NCAA tournament, 0 if not, right? Why might it be good to make the NCAA tournament? Well, there's some additional revenue, but also you're getting a lot of national exposure, right? And people who aren't really interested in sport fill out brackets, right? And so you're just getting your university's name out there, right? So I've got this 1-0 variable that I'm trying to predict. That's my Y or my dependent variable. I'm then going to say, okay, look. How does the amount of money I spend or the expenditures on that basketball program, how does that impact whether or not I make the tournament or not? Now, the way that we interpret these coefficients, whenever you have a 1-0 Y variable, well, what's my unit? So go skip ahead here for a second. Come back. So let's just say I have this regression run. I've got my coefficient on this expect back. Well, first of all, because it's really, really small, I think 0.000008. Well, why is it really, really small? I mentioned this earlier. What would a 1 unit increase in expenditures be? One more dollar. So if I spend one more dollar on my basketball program, it increases that Y variable by a really small amount, right? That kind of makes sense. Like $1 is not that big. But if we have this 1 0 variable, the interpretation of our coefficient is if expenses go up by $1, this is the predicted change in my Y variable. My Y variable, if it's a 1 0, you can think of the units are essentially probability, right? So it's increasing the probability I go from the 0 to the 1 group, or the probability that I am in the 1 group, but probably I make the tournament by about 0.00008, right? So it's pretty small, right? But if I wanted the effect of, all right, so this is like a really small, actually, I think I took this one from the second regression, which I probably should explain first. So that's kind of the idea, right? When we have this 1 0 Y variable, the coefficient is now interpreted as a change in the probability of being in that 1 group, right? In this case, making the tournament. What would we expect to sign? Well, we already looked at it. It's really small because we said 1 unit change is just $1. Now, we might also be worried about things like, well, yeah, teams that are spending large amounts in their basketball programs might be doing so because they have a lot of additional money laying around. They might be larger universities. And so just one way we can control for this, right? And this is we kind of talked about earlier. I have this omitted variable bias problem. I'm probably leaving out a lot of other things that matter. So we're not going to worry about signing this. Don't worry about this part here, but we're just going to run the second regression where we include, well, what was the size of the university? How many undergraduates did they have? Now, holding constant the size of the university or the number of undergraduates they have, now what's the impact of spending $1 additional on the probability of making the tournament, right? And we see that once I include that second variable, right, it changes my coefficient a little bit. Not a ton, but a little bit, right? So using that coefficient of 0.0, well, I got it on the next slide. If I change it from scientific notation, it's 0.000007. Right? Well, that's the effect of $1. Right? But I know that teams are spending a lot more than like $1 on their basketball program, right? Teams are spending in the millions. In fact, if I look at the range, I forget what, I think this was 2019 or 18 data. It was as high as $23 million annually, right? So to see $1 million increase isn't that unreasonable. So if I know the effect of $1, I can scale that up to say, well, what's the impact of $1 million increase? Well, it would just be that times 1 million, right? And then I'm getting some kind of more practical kind of changes, right? And that, teams are going to probably spend maybe additional $1 million. In fact, what you could do is think about if I took just the basketball programs in the top 100, if they increase their spending by 10%, that would be just shy of $1 million. Right? That's just 10% of what they're currently spending. So a 10% increase for those top 100 schools, if I spend an additional $1 or 935,000 on my basketball program, I can increase the probability of making the tournament by about 7%, right? The probability increases by 0.069 or a kind of a 6.9% increase. I could then go through and do this for every single university. Like I could do IU, right? So IU spends 10.2, so a 10% increase in their budget would be $1.2 million. So if they increase their budget by 10%, they can increase their probability by 8.8%, or the probability they make the tournament by 0.088. I could do this for Ball State, right? A 10% increase in their budget is only $150,000, right? But if they were to increase their budget by 10%, take that coefficient, multiply it by 150,000, they'd still be increasing their probability by about 1%. And you, like I said, you can go through and do this kind of thought experiment. Once you have that coefficient, you do it for whatever university you're interested in, right? Just figure out what a 10% increase in their budget would be, multiply that coefficient by that value. Any questions on this? Or keep moving here. So the kind of key here I wanted to start this example. Remember, when I have this 1 0 variable, my coefficient is now interpreted as increasing the probability that I belong to that 1 group for my Y variable. So I then kind of just throw the kitchen sink at it. I had a bunch of data layer. Well, I was getting into something else, but so I had like the team's previous tournament appearance from the year before. previous number of wins. That should be a good kind of measure of like the quality of the program. I've got revenues, right? I can spend more money if I'm making more money. So I might want to control for how much money they have kind of laying around. And then I just kind of included what we call year fixed effects. So this idea of this term of fixed effects is essentially if I think that there's something that might change my Y variable across like all universities here, maybe like different years were different. All I'm going to do is kind of set up like these 1-0 variables, right? Where it's just a 1 if the data was from a year that was in 2018, 0 if not. I would then include another one where here's the effect. I'm kind of controlling for whether or not the data came from 2019, right? And this just kind of picks up anything that might have been different in those years that was impacting my Y variable. So it's just additional control, right? So if I do that, you know, my coefficient goes down quite, yeah, it goes down quite a bit, right? It was like what, 0.0007 before, now that 7 is a 2, right? So, you know, as we include additional controls, our coefficients can change, right? We're eliminating some of that bias. Okay? So it looks like here, even though it is smaller, it's still a positive effect, right? Spending more money on my basketball program increases their success or increases the likelihood they can make the NCAA tournament. And I can say that at a very high level of confidence, right? I can reject that there's no relationship at the 99% level here. My p-value is 0.001, right? In fact, I can only say that what 99.8% confidence, right? So, you know, pretty strong evidence there's a relationship between these two variables, that spending money on your basketball program increases the likelihood you make the tournament. So what we won't do today, but we'll kind of finish up, and I'll come back to this next class as well. I want to lose, here we go. Is basically, okay, spending money on my basketball program increases the likelihood I make into the tournament. How does making the tournament increase the likelihood, or sorry, increase the number of applicants I get the following year? Because like I said, you know, this is a national event. A lot of people who aren't even interested in sports like see these names, see these brackets out there. They become national news headlines when there's a bunch of upsets. And so, for instance, who's the, like, was it last year, St. Pete's or whatever? Like, there's these universities you've never heard of until you hear like they upset in the tournament. This is just national exposure, right? Now, I always use the example, Valparaiso University. You guys know where that's at, right? If you're from Indiana, you probably do. If you told someone from California, where was Valparaiso? They'd be like, Valparaiso University? What are you talking about? I've never even heard of it, right? But if they make it into the tournament one year, right, that gets some national exposure. Maybe people go out and look. People who are prospective students might maybe go out and check out these universities, figure out, oh yeah. Or, you know, it would be like Rose-Hulman. I mean, Rose-Hulman doesn't have a program, but like they got an amazing engineering program. I didn't know that before until I kind of went to their website, right? So maybe this success that I can pay for actually has an increase in the number of applicants I get. If I get more applicants, I can be a little bit choosier, increase the quality of my student body. So we'll kind of look at some regressions that talk, you know, get this idea. Before you get out of here today, this is the last day. I'm going to use iClickers. We'll just give everybody 10 for 10 for being here today. That way I can kind of get those 3 lowest drop next week. We don't have to kind of worry about adding any additions. Okay. So just make sure you respond with any letter on the way out. Other than that, have a fun, safe weekend, and I'll see you guys on Monday.